Hello, everyone. Welcome back. This is lecture 4 for Organic Chemistry 1, and we will be talking about bond line structures, also known as just a different representation of molecules that we'll be using throughout this OChem journey that'll make life a little easier for us. And so to kind of explain this point, we'll start by looking at a structure that we will represent in a couple different ways. So the first way we can represent a structure is through a molecular formula, right? This is the simplest way to do so because molecular formulas just tell you what atoms are in the structure, but they don't necessarily tell you what the structure looks like. So if we had something like C5H10O, right? That can be a wide variety of things. And where we looked at this in lecture 1, we looked at something very similar, where we were taking a molecular formula, making it into a Lewis structure, and then we saw that there were multiple ways to draw this. So you can end up with these things called constitutional isomers. And those isomers are different molecules where the connectivity is different, but the formula is the same. There's a second way that we can actually show a molecular formula called a condensed structure. And so these condensed structure or condensed formulas are simply a different way to represent a molecular formula that tells you more about the structure. So essentially, we can get a condensed structure out of the same molecular formula that looks a little something like this. It can be CH3, CH2, CH2, CO, CH3. And the thing about these condensed structures is whenever you're looking at them, you are essentially just reading left to right, and it's telling you exactly what the molecule looks like. Right? It's telling us that on the far left, there's going to be a CH3, and then it's going to go CH2, CH2, CO, CH3. So what that's going to look like for us is we can, of course, represent this with a Lewis structure, just like we have been this entire time. But that condensed structure tells us a lot about how it's going to look because, like I said before, over here, this is going to be our CH3, right? And then next, that is bonded to what is shown in our condensed structure as a CH2. That one is bonded to a CH2. That then is bonded to a carbon, which is bonded to an oxygen. And then that is bonded to a CH3. And you may notice that if we try and draw this as it is shown there, right? There's the carbon, the oxygen, the CH3. We see that, oh, this is a little odd because at the moment, if we add in lone pairs, right, the oxygen will have the appropriate amount, right? It has an octet currently. But if we wanted to give that carbon an octet, we'd have to give it two lone pairs, which would be a -2 charge, right? And that's really quite odd. And as a matter of fact, that's actually not what we're going to see because we're not going to be drawing a structure with a molecular formula C5H10O that has a 2 minus charge, right? It's going to have to be neutral. So even though these condensed structures are really good because they tell us how things are bonded, you do have to keep in mind that sometimes things do have to still follow a couple rules. So that carbon is still going to need to get an octet. And the only way to do that is by giving it four bonds. So let's say that we give it a bond to the oxygen, we then give it a bond to that CH3 over there. There we go. Now the carbon can use another bond and so can the oxygen so that they're both neutral, both happy, and they get the electrons. So this would be an appropriate Lewis structure for that condensed formula. And so just looking at this, I'm going to use some colors as a way to just remind you of how this looks. Right, I'm going to highlight the sections of this condensed structure that belong to the formula shown up on the top right. So we can see that each of these boxes that I'm highlighting is directly corresponding to a piece of this structure, all the way up to the very end with that final CH3. Hopefully that color isn't too difficult for everyone to see. So that's fantastic. So you can use these condensed structures. Another way these can be written, by the way, is you can have something very similar where instead of having this situation where you don't know what that bonding looks like because the CO looks like it would still be in a straight linear chain, if you see it to where they put things in parentheses, that essentially means that it is off of the straight chain. So we can see all these carbons are kind of in a straight line down here, and the oxygen is kind of up above. That's what those parentheses are saying, is that it's not in a straight line with everything else. It is branched. And so branching is just essentially anytime you have a carbon that is splitting off to other atoms that are not hydrogen. So this carbon right here in the pink representation, this is technically a branched carbon because it splits off into an oxygen and that CH3. So, with that being said, we can now take a look at a different way that we can represent this because we have these molecular formulas, we have these condensed structures, we have these Lewis structures, but none of them are incredibly effective at making this really easy for us to draw. Because that Lewis structure on its own takes like a minute of time just to draw everything in, right? It's very difficult to do as the molecules start to get much larger. Instead, what organic chemists have come up with is this formula called bond line structures or skeletal structures. And so essentially, these are the way of sort of cheating out how we draw things. So, whenever we're looking at a bond line or skeletal structure, we are taking it to the bare bones of the structure. So, if we were to take this Lewis structure and convert it to a skeletal, it's actually going to look like this. And so you'll notice that that was much quicker for me to draw, and it's much easier for me to understand as time goes on. And you'll find that because as we go along, everything will be shown in skeletal structure as we go through the course. Right here at the beginning, it's very useful to think in Lewis structures, but as we start to get deeper in, we will continue to transition more and more to skeletal structure. And so, with that being said, we have to learn what we're actually looking at here. Because at the moment, this is just a bunch of lines, right? And so, the first thing that we need to know about skeletal structures is that on skeletal structures, hydrogens are implied on carbons. So, what does this mean? Well, it means that essentially we don't have to draw in hydrogens as long as they are attached to a carbon. So, if we're looking at the skeletal structure over here, we essentially have to ask ourselves, what are we actually looking at? And at the end of these lines, every time you see a little point, that is a carbon. So we can highlight this in blue. So there's the 5 carbons that we saw from that Lewis structure now in the skeletal structure, right? Each little time we see that those 2 lines come together or a line end, that is a carbon. And whenever we're looking at this rule that hydrogens are implied, it essentially means that based on how many bonds you see to that carbon, the rest are hydrogens. So up top, we see that this on the very left-hand side is a CH3. Down here in the skeletal structure, we see that this carbon has 1 bond shown. And as we know, carbon has to have 4 bonds to be happy. What that tells us is that on that carbon on the very end, even though there's only 1 bond shown, there are 3 that are implied. And those 3 are all going to be to hydrogens. So that's what we mean when we say hydrogens are implied on these carbons. Essentially, however many bonds you don't see to the carbon, that's how many hydrogens are going to be there. So if we take a look at this middle carbon here, we see that there are 2 bonds currently shown to it, right? It has these 2 right here and right here. And what that means is if there's 2 bonds shown, there are 2 bonds not shown. Those 2 bonds are 2 hydrogens. So essentially, you can do that for every single carbon that we have up here, right? We can go through and we can look at where those hydrogens would actually be based on how many bonds are shown there. And then the same thing could be said about this right here, where that carbon's bound to the oxygen. This one has all 4 bonds shown. And so because of that, there are no hydrogens there. So that's the first thing that we need to know about skeletal structure. All right, the second thing is that electrons are often implied. So once again, this is a situation where I'll redraw the structure that way it is no longer as messy. So if you remember in Lewis structures, we always draw in these electrons here, right? So the ones on stuff like the oxygen, we always show. But in something like a skeletal structure, we actually just imply them, right? We're assuming everything has an octet. And essentially, if something doesn't have an octet, we will show it. But since we don't really think that that's going to be much of a problem, we actually just imply that the electrons are there. So this oxygen, as it stands, we see that oxygen has two bonds, which of course is equal to four electrons. That means that there are four implied electrons on that oxygen, telling us that there are two lone pairs. All right. So that is another essential to these structures. But there's a third little thing, which is notice how in our first rule we did specifically state carbons, right? That is because it's not true of everything. As a matter of fact, hydrogens must be drawn on heteroatoms. So essentially what this means is if you have an atom that is not a carbon and it is bound to a hydrogen, you have to show it. And that's really, really important because if we start looking at things like, for example, if we just had an oxygen that was bound to a hydrogen, we do actually have to show that, right? So this can also be drawn just like this. But either way, in both cases, we're still showing the bond between the oxygen and the hydrogen. And that is something that you have to show. All right, you cannot imply that hydrogen is there because there is a lot of times that the hydrogen may or may not be there as we go through and learn about reaction chemistry. So, with that being said, we're going to take a look at some bond line structures. And the first thing that we're going to do is we're going to sort of practice our counting. All right, so practice hydrogen counting. So let's take a look at a structure here. Say we do this, and I'm just going to go through and I'm going to put a dot where all the carbons are. So remember, it's at the end of all of these lines, but there are some things that are drawn in, right? So keep in mind that heteroatoms still get drawn in because the ends of lines are just carbons. So there is this oxygen here in the middle of our chain, but we have a carbon here because it's the end of a line, a carbon here because it's the point of a line, a carbon here because it's also the point of a line and intersection, and carbons here, here, and here. All right. Now what I'm going to do is I'm actually going to go through and I'm going to color code each of these carbons, and we're going to take a look at how many uh, hydrogens are on each of those, right? Because essentially looking at this, there are no hydrogens on the oxygen because we would have to draw it. But we can ask ourselves for those carbons, how many hydrogens are there? So let's take a look at the blue carbon. Right, on the blue carbon, we see that there is one bond shown between it and the oxygen. That means that there are three bonds that aren't shown, so that must be three hydrogens, right? 3H. If we then take a look at the red carbon, for this one we see that there are two bonds shown. There's one bond to the oxygen, there's one bond to the orange carbon, which means that there are two bonds that are not shown, which means that the red carbon has two hydrogens attached to it. If we then take a look at the orange carbon, right, just moving left to right still, we see that at the moment there are four bonds shown to it, right? There's a bond to the red, a bond to the green, a bond to the lime, and a bond to the pink. So those four bonds tell us that on the orange carbon, that's all of its bonds, meaning that there are zero hydrogens there. All right, we can do the same for these other ones, and we see that for the pink carbon, there's one bond shown. That means there must be three hydrogens. On the lime carbon, there's one bond shown. That must mean there are three hydrogens. And then on the green carbon, there's one bond shown, which means there must be three hydrogens. All right, we're going to do this one more time, but we're going to do it with a slightly more interesting molecule. We're going to take a look at something that has some double bonds. So if we take a look at something like this, right, the first thing we want to do is we want to once again label those carbons. So we'll just go left to right. We see that there's a carbon here because it's the end of a line, a carbon here, a carbon here, and a carbon here. So looking at these, the blue carbon has only one bond shown to it, which means that there are three not shown that are hydrogens. And now the red carbon is a little different, right? This one has a double bond to the orange carbon, and that counts as two of our bonds. So there's two there, and then there's one to the blue carbon. So that tells us that this red carbon has one hydrogen on it because it has three bonds right now. It needs one more. The same thing can be said about the orange carbon, right? The orange carbon has three bonds shown. It has two to the red, one to the pink. And so that tells us that there is one hydrogen on that carbon. Last but not least, this pink carbon, it has one bond to the orange and two bonds to the oxygen, which means there's one bond not shown. That means it has one hydrogen attached to it. All right. So this is sort of how we can imply that hydrogens are there without having to actually show them. You're essentially just going to be counting the bonds, seeing how many are there, and that'll tell you how many hydrogens are there. And it starts to become easier as you go because you get used to seeing these types of structures. Now then, looking at these structures, you'll notice that we're starting to draw things a little differently, right? So we're going to take a second to sort of look at geometry of these structures. And we're going to get deeper into this as we look at hybridization. But essentially, the way you need to think of it is like this. Looking at our Lewis structures beforehand, so let's say that we were doing something like this, right? A very simple structure. It's nice because we can put all of our carbons in a straight line. But whenever we're looking at these bond line structures, right, if we convert this, we couldn't put all of those carbons in a straight line because you can imagine it would look kind of like this. And that is not necessarily a very useful, or sorry, it would look like this, but that's not a very useful way of looking at things, right? Because essentially you can't tell where any of the carbons are. And so that's why whenever we're drawing these bond line structures, we draw them at angles, right? So every line that we draw is at a approximately 45-degree angle. And that makes it to where as we draw these, you can actually see those carbons that are in the middle because we're not drawing them in a straight line. So keep that in mind as you draw these, is that you're going to be using a lot of 45-degree angles, but there are some cases where we won't, which we'll take a look at momentarily. But let's hop into looking at some more examples of how we can convert these Lewis structures into bond line structures. Right, so we're just gonna do some Lewis to bond line. And we're going to start with some simple Lewis structures and work our way up a little bit to some things that are slightly more complex. And then we're actually going to do the opposite, where we're going to look at converting from bond line to Lewis structures. So let's say that we start out by looking at a Lewis structure that looks like this, one that's very simple. All right. We can convert this into a bond line structure. And the way that I'm going to do this to make it easy to show is I'm actually going to color code these carbons as drawn in our Lewis structure, and then we will show those using our dots that we have been in the bond line structure. So what this would look like if we were in bond line is we're going to have a carbon out here on the end, right? It's going to be that blue carbon, and it has a bond to what is the red carbon. right there in the middle, right? So there's our bond between those two. And then we have from that red carbon a bond to the oxygen, which has a bond to the hydrogen that we do have to show. Because remember, one of the rules of this is that we have to show all hydrogens connected to heteroatoms. And so we can draw that one of two ways, keep in mind. We can either draw it out as the actual bond, or we can draw it out as just the OH, which makes it a little bit easier on us as well. So in the future, you'll see me quite often draw this more as the second structure that I've drawn there, just because it makes it a lot easier not having to show the extra bond between the oxygen and the hydrogen. All right, let's take a look at another Lewis structure, a little similar, but a little more complex, right? We'll have this carbon, 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 oxygen. There's a hydrogen. Once again, all right. So if we wanted to convert this into a bond line structure, we would start from that carbon on the left, and we see that we have that carbon, and it is double bonded to the second carbon. That second carbon is then single bonded to another carbon, which is single bonded to an oxygen, and we have to show the hydrogen on that oxygen. So this would be the bond line structure here. Once again, I'll help you guys out a little bit by drawing out and color coding all of these carbons for you. So the orange carbon's that one right there, red is that one right there, blue is that one there. All right, let's move on to one more example, and this is one where things get a little interesting. So in Lewis structure, this one's really going to be quite easy to see what's going on. But in bond line, some students get confused. So if we look at something like this, essentially if we're drawing this as a bond line structure, we have a carbon that is triple bonded to another carbon, right? And it's going to look like that. From here, we have now a CH3 that's bonded to that carbon there in the middle. Thing is, though, we actually don't draw this like this. Sorry, it's hard to draw it this way because it's just not correct, right? This is not a way to draw this. And the reason has to do with something that we're going to talk about um, in just a little bit, and it has to do with the geometry of things. And so we're going to be looking a lot at hybridization to discuss that. But at the moment, what you need to know is whenever you see a triple bond, it's actually going to be a linear structure following that. And so for these, sometimes you'll see the book or other drawing programs draw it like this, right? Where you can see that the triple bond kind of melts into the single bond. I, however, do not prefer to do that. I prefer to have it drawn like this. And the reason is because if we once again look at some color coding here, it makes it really easy to see where that middle carbon is, right? We have a carbon out here on the very end. Then we have that red carbon that sits right here. And then we have the yellow carbon, or the orange carbon, I guess, that sits on that side. So essentially, when we're looking at these, it makes it a lot easier to see that red carbon because if you just kind of do this, it gets a little confusing on when the triple bond ends and when the single bond actually begins. Okay, so with that being said, be mindful of that as you draw things with triple bonds, that they can be a little tricky. So let's move on and let's take a look at something that contains an interesting element. Let's take a look at something that contains nitrogen. Why not? So here would be a traditional Lewis structure of something with a nitrogen. Right, in this one we see that attached to the nitrogen are three CH3s. So what that's going to look like in our bond line structure or skeletal structure, we're going to have that nitrogen there in the middle, and it's going to have these three CH3s hanging off of it, right? And so these ends of the lines are all carbons, and they're the ones that we see over here. And again, those three hydrogens on each are implied. All right. So with that being said, this is sort of how we convert these Lewis structures into bond line, right? We're taking a look at where the carbons are, what they're connected to, and then everything else we see is going to be implied. Okay? Now then, with that being said, we can revisit an important topic from the first lecture that now is going to look a little different, but is still very important. And that is, once again, talking about constitutional isomers. So, as a reminder of these from lecture one, constitutional isomers are showing us two different structures that have the same molecular formula. And we're going to take a look back at the ones that we actually had originally drawn, which was C3H8O. At least I think it was this. Maybe it wasn't. Either way, looking at this, we're going to have three isomers of this structure. And we can draw those in Lewis, but it's actually going to be a lot easier to draw in bond line. So the first thing we can do is we can just draw a structure that should have what we want in it, right? C3HAO. So let's start out by we'll put in some carbons, right? Here's a carbon, right there is a carbon, right there is a carbon. So there's our three carbons. Here's the oxygen. And remember the oxygen needs at least a second bond to it. For now, we'll put in a hydrogen. And now we can go through and we can count, right? The blue carbon does have three hydrogens because it has one bond shown. The red carbon has two, and then the yellow carbon or orange carbon also has two. So if we count this up, we see that this is uh, 3, 5, 7, and don't forget the hydrogen on the oxygen. This is indeed C3HAO. So that is much quicker than drawing those Lewis structures, right? And drawing these constitutional isomers is also going to be really easy now. Because what you can do to draw constitutional isomers is remember that we have to have the same formula, but different connectivity. And that is where the key to it is, right? Different connections. So what we can do is we can say, all right, well, in the case of this first structure here, the oxygen is connected to the orange carbon. What if instead we just connected it to the red carbon, right? We can move it over to that red carbon. And now look at that. If we were to actually look at this and once again do a quick count, we see that the blue carbon has three hydrogens. The red carbon has three bonds, which means it only has one hydrogen. The orange carbon has three hydrogens. And then we can't forget the one that's right there on the oxygen. That is also C3HAO. And all we did was move that oxygen from one carbon to another. We can do the same thing once again where we're taking a look at, hey, what happens if we move it to the blue carbon? Right? So this would be moving it over to the blue carbon. And at first, this sounds fantastic, right? Looking at it, we have once again C3HAO, but this is actually not unique. What I mean by this is the same as the one over here. The only difference is we've now mirrored it, right? If we were to put these two side by side, looks a little bit like that. It's like this thing is staring in a mirror, right? And if it's staring in a mirror, that just means all we have to do is we can rotate this guy around a vertical axis, right? All it is like flipping over a piece of paper, and it ends up being the exact same as the one on the left. So whenever we're looking at these constitutional isomers, you have to start recognizing things that are the same versus things that are different. The one in the middle is clearly different, right? Because unlike the other two that are connected to these carbons that only have two hydrogens, it ends up being the case where the one in the middle is very unique. It is connected to the carbon in the middle, and is only connected to the carbon with one hydrogen. All right. With that being said, though, this is not the only set of isomers that we have for this structure. Another one that we can see is, well, if we can't move that oxygen to be attached to any of these other carbons, what if we could have it attached to multiple carbons, right? We can put it in between some of them. So if we do that, we could see as an example where we have something like this, right? In this case, we've kind of shoved the oxygen between the red and orange carbons. And in this case, if we were to do a quick count of hydrogens, we would see that this indeed is C3H8O. And as a matter of fact, this is the last isomer that we can make of this, because if we were to try and put the oxygen between the red and the blue carbons, we would see that we have once again made something that is not unique, right? It can essentially be flipped in a very similar manner to the one that we saw before to make it look like the same thing as something else. All right, so constitutional isomers in these bond line forms are very important to be able to distinguish, and it's also very important to be able to tell what you've already drawn versus what is a different compound. And we'll start to see this come a little bit in a couple of weeks when we start looking at things that are going to look very similar, but you're going to have to be able to tell when they are actually different. All right, let's take a look at a second set of constitutional isomers because there is another lesson that we can learn from these. And this one is going to be C3H5N. And I'll tell you right off the bat that this has four isomers. So let's take a look at what those actually are. C3H5N, we can actually do the same thing that we did last time, where we can just take the three carbons, put them in there, and then slap the nitrogen on the end. And once again, when we're thinking about this nitrogen here on the end, we want to make sure that it has all the bonds it needs. So giving it two hydrogens would give it three bonds. But then if we're doing a quick count, we would see that we have much more than five hydrogens, right? Because just alone, this blue carbon here on the end has three, which means that we'd already be at C3H5N. And that's not even counting the ones on the red and the orange carbons. So if we're taking a look at what those are, this right here would have a formula of C3H, that'd be, I think, 7, right? 3, 5, 7. This would be 9. C3H9N. So we have to find a way to decrease the number of hydrogens that are in this. And the way we can do that is through adding in multiple bonds, right? So if we take a look at adding in some multiple bonds, we can add in something like a triple bond. So if we put that between a couple of carbons, that would be now the blue and the red carbon. We then have that connected to the orange carbon, and then we have our nitrogen. So this now, if we take a look at it, the blue carbon has three bonds shown, so it only has one hydrogen. The orange or the red carbon has all four bonds shown, so it has zero hydrogens. And then the orange carbon has two bonds shown, so it has two hydrogens. And then, of course, we can't forget that nitrogen does have two hydrogens shown. So this is now the appropriate C3H5N. So now we can take this and we can start to look at different isomers of this form. So I just recognized that I accidentally said this was 4. That is not true. Don't even look at that. That is 4 if it was C3H7. So I apologize. But moving forward, we can take a look at a isomer of this. We can ask ourselves, well, just like beforehand, when we were moving around that oxygen, what if we connected the nitrogen differently? So we can't put it on the red carbon because the red carbon already has four bonds, but the blue carbon, we could put it there, right? And if we do so, it does end up giving us what we want. Because essentially by putting the nitrogen onto the blue carbon, that means that there's no longer a hydrogen there, but now there's going to be an extra hydrogen on the orange carbon. right? So this right here, we now have three hydrogens on the orange carbon, and then we have those two hydrogens on the nitrogen. So this is another isomer here. One of the interesting things that we can do is we can also move those double and triple bonds around, but not in the same way that we would move this nitrogen. We can actually move them a little separately. So let's say we were looking at that first structure again, and instead of having a triple bond between red and blue, let's say we had a double bond between red and blue. And then we said, okay, well, if we have a double bond between red and blue, we need another double bond, right, to make sure that we don't have too many hydrogens. What if we put it between the nitrogen and the orange carbon, right? In this situation, we see that we've changed the connectivity by just moving around where those bonds are, but we still end up in the appropriate situation where now the blue carbon has two hydrogens, red has one, orange has one, and the nitrogen has one. That's C3H5N. So this is another interesting way that we can do this is we can move these double bonds around. But that's not the only way that we can actually have less hydrogens than the maximum, which is saturated. We can also go through and we can make what are called rings. So we're going to start seeing these a little more often as time goes on, where rather than having these straight chains, right, because that's what we've been looking at a lot of, we can actually have what is essentially ring systems where it's a cyclic molecule. So in this situation, we can say, what if we went through and we put all of these elements, all these atoms, to where they're connected to one another, right? We have four major atoms here, the C's, three carbons and one nitrogen, and we can put those into a square, all four of them. And looking at this, we see that, okay, well, if we put the one hydrogen on the nitrogen that we need, the formula for this comes out to be C3H7N. But if we also give it a double bond, we then end up with the appropriate count, right? Because if we have blue, red, orange, we see that orange has one hydrogen, red has one hydrogen, blue has two hydrogens, and the nitrogen has its hydrogen. So that's another C3 H9 or C3H5N. And this isn't the only ring that we can make, right? Rings essentially substitute a double bond, but we can also make a ring structure that looks a little bit like this, where we have now a three-membered ring, which is a triangle. So that can have the nitrogen in it. We just need one more carbon. We can also give it a double bond. And so here we once again have C3H5N. Once again, do the counting. And you can continuously do this, right? There are a large number of constitutional isomers that you can get out of these small molecules, right? So this is a lot of isomers. Normally, if I'm going to give you questions like this on your quizzes or exams, I'll tell you exactly how many isomers there are. That way you know how many you need to draw. And your assignment for this week does have a question about constitutional isomers where you're looking at drawing them and you're looking at covering all of the possible constitutional isomers that there are there. All right. Now, that being said, um, from now on, we're going to start trying to shift towards drawing things in this bond line structure form. And again, it's going to make things very, very easy. And so one last thing that I'll end off with is actually drawing one last bond line structure. And it's one that's going to come quite handy as time goes on. And that is going to be the structure of benzene. We're actually going to do a benzoic acid. And the reason I want to draw this is I just want to, again, draw your attention to how important it is to be able to count all of the atoms that you go through with these because it is incredibly important to know what you're doing when you convert these from these bond lines or the Lewis structures to bond line structures. Because something that looks like this in Lewis can be very easily represented, right? We have to get all six of those carbons into a ring. So start practicing your hexagons because they're going to come up. So this is what it would look like. And we know we have a double bond between these two carbons, double bond between these two, double bond between these two. And this one here is connected to a carbon that is connected to these two oxygens, and that oxygen has an OH. And so essentially, as we go on, we're going to start representing things like this. That way we can make our drawing lives easier in the future. So with that being said, the quiz next Wednesday, because remember we have Monday off for Labor Day. There will be no video lecture that you'll need to watch then. It will be over everything from the beginning of class to like through resonance and to this material. You are expected to be able to complete the quiz in about 20 minutes, but you will have a time limit for 30 minutes. And essentially, it will be covering all of this in about 4 to 5 questions as best as possible. So, thank you for watching, and hopefully, this gives you a good idea on how we're going to draw these things in the future.